What is meant by saying that the potential difference between 2 points is 1 volt? So for the potential difference to be equal to 1 volt, we have 2 points. See, we have point A and we have point B. And from point A to B, I move a charge of 1 coulomb. And as I move a charge of 1 coulomb, if I do work equal to 1 joule, then the potential difference between A and B is said to be 1 volt. So if 1 joule of work is done to move 1 coulomb of charge from one point to another, the potential difference is said to be 1 volt. Which means again, if I have point A and I have point B, and in moving 1 coulomb of charge, if I do work of say 3 joules, now in this case the potential difference between A and B will be 3 volts. So potential difference V is work done per unit charge. Define electric power. What is its SI unit? Now power is also the rate of doing work. So the rate at which electric energy is dissipated or consumed in an electric circuit is called electric power. So how much of energy is consumed per second is power. So I repeat again, rate at which electric energy is dissipated or consumed in an electric circuit is called electric power. So the important word here is rate at which. The SI unit of power is watt. Now we know the formula of power is V into I, voltage into current. Now if I equal to 1 ampere and your voltage equal to 1 volt, then we know the P equal to 1 into 1, which is equal to 1 watt. So how would you define 1 watt? It is a power consumed by a device that carries 1 ampere of current, this 1 ampere of current, when operated at a potential difference of 1 volt. So then we get P equal to V into 1. This is 1 volt, this is 1 ampere, so power becomes 1 watt. It's the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. And to repeat again, what is electric power? Normally power in physics is rate of doing work. But in electricity, it is a rate at which energy is consumed. Energy and work are interchangeable. So it's a rate at which energy is consumed. Electrical energy is consumed. A wire of resistivity ρ is stretched to twice its length. What will be its resistivity? So suppose I have here a thick wire and it is stretched to twice its length. That means the length becomes much longer. If this is now L, this will become 2L. Now resistivity depends, if you remember the factors on which resistivity depends, it depends on nature of material and on temperature. So in this case we have seen the nature of material has not changed. If this was copper, this again is copper. If this was aluminium, this again would be aluminium. So the nature of the material has not changed, nor has the temperature. So what do you expect the resistivity? The resistivity in this case will remain same. The resistance will change. The resistance will change, but resistivity will remain the same. Define ohm. Now first we know that ohm is a unit of resistance. This you need to remember. And by Ohm's law, resistance, we know V equal to IR. So R equal to V over I, which means if voltage is 1 volt and the current is 1 ampere, then the R becomes 1 volt over 1 ampere and the resistance becomes 1 ohm. To explain this, I'll take a wire, and this wire of course is now connected to a battery. I'll just make it continuous. It has to be continuous. This is the wire, say AB. How will I explain what is 1 ohm? Here I'll apply a potential of 1 volt. We take V equal to 1 volt. So I put 1 volt, and when I apply a potential of 1 volt, immediately a current of 1 ampere begins to flow through the wire. Then I can say that the resistance of this wire is 1 ohm. So we could define 1 ohm is if potential difference across the two ends of the conductor is 1 volt and the current is 1 ampere, the resistance is said to be 1 ohm. Name the device that maintains a potential difference across the conductor, and that is a cell. Cell maintains potential difference, and that's how current then begins to flow. A cell is denoted like this. This is the positive. First is the positive and then is the negative. But what is a battery? Battery is a collection of cells. And it is positive, negative, connected here, positive, negative, connected, positive, negative, so on. This is a battery. Here will be the positive, this will be the negative. It helps to maintain a potential difference across the conductor. So here is the wire. It is connected, say, to this cell, and hence this becomes positive and then this becomes negative. It maintains a potential difference, and because of this potential difference, then the current begins to flow. Define resistivity, write its SI unit. So first let us see what is resistance equal to. Resistance equal to rho L by A. It is a formula where rho is resistivity. So L is the length of the wire and A is the area of cross section. So if I want to know what is resistivity, I will take length, say 1 meter, and area of cross section 1 meter square. Let me draw this wire. So I'll take a wire whose length is, this length is 1 meter, that is L equal to 1 meter, and this area of cross section is equal to 1 meter square. So area equal to 1 meter square. Then what happens to this formula? So R equal to rho, the length is 1 and the area of cross section is also 1. So R equal to rho. Now we can define resistivity. Resistivity is the resistance of a wire having length 1 meter, area of cross section 1 meter square. So the definition of resistivity is the resistance of a wire of length 1 meter. That's what we have taken. L equal to 1 meter. And area of cross section 1 meter square. This is what we have taken. Area of cross section 1 meter square. Then we got resistivity equal to resistance. To get onto the unit of resistivity, we know that R equal to rho L by A, which means now rho equal to RA over L. So rho equal to, now resistance is ohm, area of cross section meter square, length is meter. So we cut this. So resistivity unit is ohm meter. So when they're asking you what is the unit of resistivity, it is ohm meter. And does it vary with temperature? Yes, it does. It increases with temperature. When temperature increases, resistivity also increases. Will current flow more easily through a thick wire or a thin wire? Now, wherever the resistance is less, that's where the current is going to flow more easily. So here I have a thick wire, and in the next case I have a thin wire. So you will definitely agree that the resistance here, say wire A, and this is wire B. Resistance of A will be less than resistance of B. And why? Which factor are we considering here? Thick wires have always less resistance because resistance is inversely proportional to area of cross section. Thick wires are thick and they have less resistance. Thin wires have less area of cross section, so they have more resistance. So since the resistance of A is less, therefore the current in A will definitely be more than the current in B, because A has less resistance. Let's put it out here. This has less resistance, this has more resistance. Less resistance means more current, and this will have less current. Thick wires have less resistance, thin wires have more resistance. A wire of 10 ohms resistance is drawn out so that its length is thrice its original length. Calculate its new resistance. So here I have a thick wire, and in this thick wire, say the length L is L, and the area of cross section is A. Now it is stretched to 3 times its length. So if you're stretching it to 3 times of length, it's going to be longer and thinner. So now the length will be 3L, and they'll have a new area of cross section. Let us call that as A2. Let's call the first area of cross section as A1. Let us see what is the new area of cross section. Now this is the same material that is stretched. So the volume in case 1 equal to volume in case 2. Now volume, you know, is area of cross section into length, and here also volume is area of cross section into length, which is 3L. So here A1 over A2 will be equal to 3 over 1, which means if A1 is 3x, your A2 will be 1x. So for this A1, now I'm going to rub it out, and I'm going to write this as 3x, and here this will be 1x. What happens to the new resistance? The resistance out here, the first resistance rho L over A, the second resistance will be rho 3L, because now the length is 3L and the A is 1x, and this 2, the A here, I've got to change it to 3x, because see, the A is 3x. Now I'll do R1 by R2. R1 divide by R2. My R1 is rho L over 3x divide by rho 3L over 1x. So R1 by R2, rho L over 3x, the division becomes multiplication, 1x over rho 3L. So R1 over R2, if you cancel everything, becomes 1 by 9. Now we know the R1 is 10 ohms. The first resistance was given as 10 ohms. We have to find the new resistance. So 10 over R2 equal to 1 by 9. So 10 into 9 equal to R2. 90 ohms will be the new resistance. The resistance from 10 ohms will increase to 90 ohms. So the new resistance now is 10 ohms. The material has not changed, the resistivity has not changed, but why has the resistance changed? Because the length has increased and the area of cross section has decreased. On what factors does the resistance of a conductor depend? and that we've already know. How many factors? I think there are 4 factors. 1, 2, 3. The first factor is the length, and for the length you'll say resistance is directly proportional to length. Longer the length, more is the length, more is the area, or more is the resistance. Then other one comes area of cross section. And how does it depend? Resistance is inversely proportional to area of cross section. More is the area of cross section, less is the resistance. That is why we said thick wires have less resistance because the A is large, and for thin wires the A is small, so more resistance is inverse. It goes in opposite direction. It also depends on temperature. Higher is the temperature, more is the resistance. And last, it depends on the nature of the material or the resistivity. And we have seen that silver is one of the best or have least resistance and hence carries maximum current. What is a voltmeter? How is it connected in the circuit? Now, voltmeter is a device that measures potential difference. So it measures potential difference across 2 points in an electric circuit. And remember, to measure potential difference we have to connect it in parallel, because in parallel the potential difference remains constant. Here is the circuit. If I want to measure the potential difference across AB, I will connect it in parallel. So I will connect here the voltmeter out here. If I want to measure the potential difference in CD, I will connect my voltmeter in parallel here. So voltmeter is always connected in parallel. Connected in parallel. Three resistors R1, R2, R3 are connected in parallel. Find the equivalent resistance. So here we have R1, R2 and R3 are connected in parallel to a battery V. So when the current reaches at this point, it is now going to break up into 3 parts: I1, I2 and I3. I1, I2, I3. This is the main current I. So we know that I equal to I1 plus I2 plus I3. Now for R1, Ohm's law, V equal to I1 R1. The voltage remains the same. So I1 equal to V over R1. Now for R2, Ohm's law, V equal to I2 R2. The V remains the same because it is in parallel. So V over I2 equal to V over R2 equal to I2. And for the last one, we have for R3, V equal to I3 R3. So V over I3 or V over R3 equal to I3. Now when we put the values here, we put V over R. R is the effective resistance. For I1, I will put now V over R1. For I2, I will put V over R2, and for I3 I will put V over R3. So I take V common out, so I get 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. What is electric current? And we have defined here electric current is the rate of flow of charge, electric charge. What do you understand by conventional direction of flow of current? Now here in the first diagram, we see that there is a battery here, and this battery there is a positive, the negative, and current begins to flow from negative to positive. So here we have the negative, and the current means electrons, not current. it was electrons. Electrons flow from negative to positive. But we imagine that there is a current flowing from positive to negative. Because if you remember, I explained to you earlier, everything in nature flows from positive to negative, from high to low. So here electrons are flowing from negative to positive. So we imagine that the current is flowing from positive to negative. So again, in the next diagram we see that the actual electrons are flowing from negative to positive in this direction. But the flow of current is said to be in the opposite direction. That is from positive to negative, in the opposite direction. So to summarize this, if electrons, the actual flow of electrons are from negative to positive, but current, we imagine current flows from positive to negative. For the next is what is the unit ampere defined? So ampere is a unit of current. It's a unit of current, and to define it, we know that current I equal to Q over T. So if Q is 1 coulomb and time is 1 second, then I equal to 1 over 1 coulomb over 1 second, that is 1 ampere. So 1 ampere is the current when 1 coulomb of charge flows per second. So when 1 coulomb of charge flows per second, the current is said to be 1 ampere. So repeat again, the flow of charge is always, the flow of electrons is always opposite to the flow of current. Name 2 factors on which electrical energy consumed by an electrical appliance depends. We know electrical energy consumed is power into time. So the 2 factors on which electrical energy consumed depends is the power of the device, the rate at which it takes up energy, and the time for which the device is kept on. However, we know that P is also VI. So for P we put VI, and this is into T. So you can say the power also, energy depends on voltage and the current drawn by the device. Which of the following cases have more electrical energy consumed? 1 ampere current passed through a resistance of 300 ohms. So in the first case 1, my current is 1 ampere, the resistance is 300 ohms, and I want to know the energy consumed for 1 hour. So time is 1 hour, which I will make 60 into 60 seconds because I need to work in second. So here I've got to find the energy. Energy, in this case I'll use the formula I square R T because current is given to me. So 1 into 1, resistance is 300, and this is 60 into 60, 3600. So this is the energy, and it works at 180 with 1, 2, 3, 4 joules. Now for the second case, 2 amperes pass through 100 ohms. So case 2, amperes is current and resistance is 100 ohms. The time is the same per hour. Per hour means 1 hour is 60 into 60 seconds. Same formula, equal to I square RT because current is given. I is here 2 into 2, R is 100, and this is 60 into 60, 3600. Here it is 144. So we agree that in the second case, so many joules. The energy consumed more will be in the second case, in case 2. What is meant by electrical resistance of a conductor? Now, as the electrons flow through a conductor, they constantly bump into the atoms, and hence they cannot easily flow. Like in this case, we've seen a conductor and there are this positive nucleus, and as these electrons now are flowing through this wire, as they keep flowing through the wire, they are constantly attracted by the nucleus, because the nucleus is positively charged. So the nucleus attracts it. They also sometimes hit the nucleus, which is a very small possibility, but they do hit the nucleus. So the electrons are not free to move through the conductor. They experience a resistance. This resistance is called electrical resistance. So the resistance of a conductor is a property of the conductor to resist the flow of current. Now, to repeat again, why do we get this resistance? What is it that tries to block the flow of current? The positive nucleus. The electrons are negatively charged and the positive nucleus keeps on attracting it. And also the electrons could bump into the nucleus, could hit the nucleus as it is moving. Hence, they are not free to flow. This resistance is called electric resistance. A wire of length L and resistance R is stretched to double its length, and the area of cross section is halved. What will be its resistance and what will be its new resistivity? Now, new resistivity will answer first. Resistivity depends on two factors, on nature of the material and temperature. When this wire is stretched, there is no change in nature, there is no change in temperature. So you don't expect the resistivity to change. The resistivity will remain same, because the material does not change, the temperature does not change. Let's go ahead and see what happens to the resistance. So here first the length is L and resistance is R. So we'll write case 1. Here the length is L, resistance is R. So that its length is double. Now in case 2 the length is double, so it became 2L. This is resistance 1. The resistance changes, we'll put R2. Area of cross section is halved. So if this was A, now the area of cross section will become A by 2. This resistance formula, rho L by A. Here resistance R2 will be rho. Now the L is 2L and the A is A by 2. So we need to do R1 by R2. Let's first just tackle this. This is rho 2L divide by A by 2, right? Because the division is at this point here, this division. So the division becomes, so now we have, this is rho 2L into 2 by A, which is rho 4L by A. This is your R2. So our R1 is rho L by A divided by R2, rho 4L by A. I'll continue with this. So R1 by R2 equal to rho L by A. The division at this point, this division I'm going to make multiplication, and then I take reciprocal, so it becomes A over rho 4L. So R1 by R2, this cancels out, so I get equal to 1 by 4. So I see that the R1 is 1 R, say, and the R2 is 4R. So what has happened to the resistance? It has increased 4 times. So I say here resistance increased 4 times. Three resistors R1, R2, R3 are joined in series. Find the equivalent resistance. So we have R1, R2, R3 joined in series, one after the other. and we know in this case the current flowing will be the same. The current flowing I will be the current flowing through R1, same current will flow to R2, same current to R3. However, there will be a change in the voltage. If this voltage is V, just V I'll put, then the voltage across V1, potential difference V1, V2 and V3. Now here V equal to V1 plus V2 plus V3. Now for R1, and we'll calculate then for R2 and then for R3. For all of them the current is the same, because in series current remains same. Here we have V1, Ohm's law, I R1. Here V2, I R2, the current is same. V3, I R3, current is same. So V equal to IR, I is effective is a current, R is the effective resistance, I1, IR1, IR2, IR3. I take I common out, so R equal to R1 plus R2 plus R3. State Ohm's law. The potential difference V across the ends of a metallic wire in an electric circuit is directly proportional to the current flowing through it, provided the temperature remains constant. So here they say the potential difference directly proportional to current, provided temperature remains constant. More is the potential difference, higher is the current in the circuit. Now to experimentally to prove it, this is a picture of the activity from your textbook. So here you read the activity. This comes for good 4 marks in section D, so you need to study it. So you arrange the circuit diagram, and then you just keep changing the voltage. Like here, first use only one cell as a source in the circuit and note the reading in the ammeter. So maybe we'll just use 6 volts. And after using a 6-volt battery, we find that the current is like 2 amperes. So we will find 6 over 2, and that becomes 3. So here we get 3. Then we put another battery. So 6 plus 6, we have 12 volts. Now after we have 12 volts, we found the current also doubles. The current becomes 4 amperes. So here again we divide 12 by 4, we get 3. Now we add yet another battery. So 12 plus 6 became 18 volts. And then we find the current now when we measure becomes 6 amperes. So 18 over 6, again 3. And now again we will put another battery. So 18 plus 6, and that is 24 volts. And we find here now the current will become 8 amperes. But what remains constant? Voltage over current, that is 8. This remains constant because this is resistance. It remains constant for a wire. So this is how you go about doing the activity and reading the steps. This is given on page 204, and there also the diagram is given of you plot the graph of V against I, and when you plot the graph of V over I, it comes as a straight line passing through the origin.